Okay, block diagrams are a useful way of describing dynamic systems. So we sort of know the simplest one, but let's imagine now that we have a signal like this, and we're going to, so here's input u of s. We have g1 of s as a transfer function, and we follow that by a second transfer function like this, g2 of s. And so here's the output y of s. Okay, so this is called the cascade. Later we'll see control systems that use this sort of cascade form. This is called cascade or series form here. Okay, and so in this case what we could do is we just write that y of s is equal to g2 of s times g1 of s times u of s. And so the transfer function of this series combination of two transfer functions is just found by multiplying g1 and g2 together. Okay, so we end up with this guy. We also might have parallel form. Okay, so g1 and g2 are in parallel. And we're taking their output and we're adding it together to produce y. We could write y of s is going to be equal to g1 of s times u of s plus g2 of s and u of s. And so in terms of the transfer function, we could write that y of s over u of s is equal to g1 of s plus g2 of s, right? Right? So in series form, we're multiplying the two transfer functions together. In parallel form, we're just adding them together. Okay? Now these are really simple, but we use them to build up more sophisticated block diagrams. And the one that's going to be most important for this class is a feedback system. Okay? And this is called negative feedback, and I'll explain why that is in just a minute here. So here's g1 of s. Here's g2 of s. And summing junction. And here's the output. Okay, now I'm going to change my terminology a little bit. I'm going to call this R of s, and that'll the reason why it's called R of s will make sense in a little bit. I'll explain that a little bit more. And the thing I'm going to do is I'm going to note here that this is negative feedback. So rather than taking the sum of these two signals here, I'm taking the difference between R of s and the output of g2 of s. Okay, and I'm going to call this signal here E of s. Okay, it's called the error signal, and I'll explain why that is in just a minute. First, I'm going to write down what the transfer function is for this negative feedback system. Okay, and so we can see that by the way the block diagram is written, E of s is equal to R of s minus g2 of s times y of s. Okay? And then, so that's sort of the definition of our error signal. Okay, and so then let's look at what y of s is. Well, y of s is g1 of s times E of s, right? Let me write that in black down here. Y is equal to g1 times E. Okay, and I'm going to substitute in the expression that I found for E. So I write it as g1 of s times R minus g2 times y. Okay, so let me go ahead and go like that. Okay, and so now what I can do is I'm going to collect all the terms that involve y on the left-hand side, right? So clearly I have g1, g2 times y on the right-hand side, so I'm going to push that over to the left. And so when I do that, I get 1 plus g1, g2, whole thing times y is equal to g1 times r. Okay, so you see what I did? I took it's minus G1, G2 over here, and I pushed it over to the left-hand side, so I get plus G1, G2 when I put it on the left-hand side. And so now what I can do is I can solve for the transfer function. Y, the output over the input, Y over R is equal to G1 of S divided by 1 plus G1, G2. Okay, this is the transfer function for negative feedback. Okay, in other words, what this is it's a closed loop transfer function because I have a closed loop from the output to the input, and because it's negative feedback, it turns out that I get a plus sign here, right? That's why this thing was negative over here, right? And then when I pushed it over to the left-hand side, it became positive. So this is the transfer function for negative feedback. Now often, instead of having a transfer function in the feedback loop on the bottom here, instead of having a transfer function there, we might just have nothing, right? So if we replace G2 with a 1, right, then I don't have to draw a block there at all. And 1 is a unit, right? And so I call that unity feedback. Okay, so unity feedback is when G2 of S is equal to 0. Okay, so there is nothing in the feedback loop, nothing in the return path. There's basically a 1 or unity in the feedback loop. Okay, so this is just terminology. Now let's talk about how this is like actually used. Okay, so the thing I think is like the useful way to think about this is let's think about like a thermostat system. So it's something that we are all kind of familiar with as a control system. So what I'm going to do is imagine that we have like a heater and we have like a temperature sensor. So the heater is the input to our thermal system, and we have a temp sensor over here. Whoops, not temp sensor. There's a temp sensor over here, and so I'm going to call this the input to the thermal system is U, and the output is Y. Okay, so that's the thing that we want to control. And I'll call this guy GP of S. So GP is the plant, it's the thing that we want to control. Okay, and so the idea in this temperature regulation system or thermostat system is we want to make the temperature go to a desired set point, right? So we're going to use the heater to do that. We'll turn on the heater to make the temperature go up, and we use the temperature sensor to measure the temperature, okay? But the idea is what we're going to do is we want to make Y go to a desired set point. So let's say what the goal is here. So I'll write it like this. This is the thermostat. So our goal, make Y, which is the temperature, go to a desired set point. Right? This is what you're doing when you set the thermostat in your house, okay? And I'm going to call that set point R of S. It's called a reference, right? R means a reference. And so to do this, what we want to do is we're going to take the temperature sensor signal, and we're going to bring it back around, and we're going to compare it to the reference. So here's R of S going into this summing junction, okay? And this E of S is the error, right? So ideally, the error is equal to 0. Let me make this a little bit bigger here. So the error signal, E is equal to R minus Y. And so our goal, we could restate this. We're saying that we want to make Y be equal to R. In other words, we're going to make the error go to 0. So we're going to use a controller to drive I'll write it in the time domain, e of t to 0. Okay, and so eventually, when e of t is 0, that will mean that e of s, the Laplace transform of the error, is also going to be 0. Okay, so that's the goal of our control system, to make the error signal to be 0, or at least very, very small. Like if we think about it as a temperature system, maybe we don't care if we have like 1 degree or 2 degrees we probably care about, but 1 degree is, I'm sort of happy with, if I set my thermostat to 68, then I'm happy if it's 67 or 69, so I could tolerate a little bit of error there. So one way to do this is to feed the error into a proportional controller. Okay, so this thing here, I wrote plant here, and so I'm going to write above this K, I'm going to write the controller. Okay, and I have to go to the next page, but so you can see the idea of this controller, it's just a K. It doesn't have a K of S here. And so what I'm saying is that the output of the controller is U, right, from the block diagram. The input is E. And so I'm going to write down here, I have a proportional controller. That says that U is proportional to the error signal. Okay, so K is a constant. And we call that the proportional control gain. Okay, so this is basically maybe the simplest example of a feedback control system. We have a thermal system, which is maybe it's a house or a room. Okay, it could also be an oven, for example. We have an input to that system, which is the heater, that's U, and we have an output, which is the sensor, Y of S. Okay, and what we want to do is we want to make that temperature go to a desired value, which is specified by the reference R. So we take Y and we compare it to R. That allows us to calculate the error. And then what we're going to do is we're going to just make the signal to the heater proportional to the error. So when the error is large, we're going to apply a lot of heat. And when the error is small, we're going to apply a little bit of heat because we're close to the desired set point. And eventually, actually, when the error goes to 0, we could just turn the heater off, right? So does that make sense? This is a proportional control system. And so now what we could do is, now that I've kind of given you this example, we can go back to sort of what you know about the things that I told you. So cascade form, you see that when two blocks are followed by each other, we multiply them together, okay? I'm not going to use parallel form at this time. And then I told you about negative feedback, okay? So we ended up with something like this, where the transfer function that's in the forward path, okay, and the transfer function that's in the return path will end up giving us a closed loop transfer function that looks like this, okay? So I can use those two things together. So I look at my proportional control system, and I see I have a cascade of two things in the forward path, and I have a unity feedback in the feedback path, and so I get my G2 is just a 1 here, okay? So if I look at my proportional control loop, so if we compare to the arbitrary sort of negative feedback loop, we could write that G1, the forward path, is equal to K times GP. That came from the series form, right? And G2 of S is just a 1. So this is what it means for it to be unity feedback. Okay? Okay? And so what I can do is I can look back, I'm going to jump back here, and I look back at y over r, this is the general form, g1 over 1 plus g1, g2, okay? So I'll go ahead and write that out. Y over r is equal to g1 over 1 plus g1, g2. And so in this specific case, I've got k gp over 1 plus k gp of s. So this is the closed loop transfer function for a proportional control system. Closed loop transfer function for a proportional control system. Okay? In the next section, I'm going to expand upon this a little bit.